Hello everyone, my name is Agwin Kennard Parasian Turnip. Today I will present my task for building information modeling midterm exams. As you can see on the screen, my presentation today is BIM for subcontractors and fabricators. First, preliminary. The professional gap between designers and builders that became pronounced during the European Renaissance has continued to widen over the centuries. While building systems have grown increasingly complex and technologically advanced, over time, builders become more and more specialized and began to produce building parts offsite, first in craft shops and later in industrial facilities for subsequent assembly on-site. As a result, designers had less and less control over the entire design. In traditional practice, paper drawings and specifications prepared by fabricators for designers fulfill additional vital purposes. They are a key part of commercial contracts for the procurement of fabricators' products. They are used directly for installation and construction, and they are also the primary means for storing information generated through the design and construction process. For subcontractors and fabricators, BIM support the whole collaborative process of the design, development, detailing, and integration. In many recorded cases, BIM has been leveraged to enable greater degrees of prefabrication that was possible without it, by shortening lead times and deepening design integration. Next is beyond these short-term impacts on productivity and quality, BIM enables fundamental process change because it provides the power to manage the intense amount of information required of mass customization, which is a key precept of lean production. As the use of lean construction methods become widespread, subcontractors and fabricators will increasingly find that market force will compel them to provide customized, prefabricated building components at price level previously appropriate for mass-produced, repetitive components. In manufacturing, this is called mass customization. And second is type of subcontractors and fabricators. Subcontractors and fabricators perform a very wide range of specialized tasks in construction. Most are identified by the type of work they do or the type of components they fabricate. For a discussion of the ways in which they can exploit them, the degree of engineering design required in their work is a useful way of classifying them. Looking beyond raw materials, building components can be classified as belonging to one of three types. First is made stock components, such as standard plumbing fixtures, drywall panels and studs, pipe section, and the like. Second is made to order components, such as pre-stressed hollow core planks, windows, and doors selected from catalogs. And last is engineered to order or EDO components, such as the members of structural steel frames, structural precast concrete pieces, facade panels of various types, custom kitchens, and other cabinetware, and any other component customized to fit a specific location and fulfill certain building function. Next is the benefits of a BIM process for subcontractor fabricators. EDO components in building construction has some product flow process. The process has three major parts: project acquisition, preliminary design and tendering, and detailed design, engineering and coordination, and the last is fabrication, including delivery and installation. The process includes cycles that allow the design proposal to be formulated and revised repeatedly if necessary. This typically occurs at the detailed design stage, where the fabricator is required to obtain feedback and approval from the building's designer, subject not only to their own requirement, but also to the coordination of the fabricator design with other building systems also in development. And this is the typical information and product flow for a fabricator of EDO components or engineer to order component. First phase is building design, and the close phase is operate and maintain building. This part of flow is have so many ways and uh, and to operate and maintain building. This flow has three major parts. The first, project acquisition, detailed design, and fabrication. Next is marketing and tendering. Preliminary design and estimating are essential activities for obtaining work for most subcontractor fabricators. To win a project with a profitable price require precision in measuring quantities, attention to detail, and the ability to develop competitive technical solutions, all of which demand significant time investment by the company's most knowledgeable engineers. Generally, not all tenders are successful, and companies are required to estimate more projects than are eventually performed, making the cost of tendering a sizable part of the company's overhead. BIM technology aids engineers in all three of these areas, developing multiple alternative detailing solutions to a reasonable degree and measuring quantities. For marketing purposes, and persuasive power of a building model for a potential client is not limited to its ability to provide a 3D or photorealistic image of a proposed building design, as is the case for software that is limited to 3D geometric modeling. Its power lies in its ability to adapt and change design parametrically and better exploit the embedded engineering knowledge, allowing for more rapid design development for satisfying clients' needs to the greatest extent possible. Next is reducing production cycle times. The use of BIM significantly reduces the time required to generate sub-drawings and material take-off for procurement. This can be leveraged in three ways. First, to offer a superior level of service to building owners for whom late changes are often essential by accommodating change later in the process than is possible in standard 2D CAD practice. Making change to building design that impact fabricated pieces close to the time of fabrication is very difficult in standard practice. Each change must propagate through all of the assembly and shop drawings that may be affected, and must also coordinate with drawings that reflect adjacent of connect components to the pieces that change. Where the change affect multiple building systems provided by different fabricators or subcontractors, coordination becomes far more complex and time-consuming. With BIM platforms, the changes are entered into the model and updated erection, and shop drawings are produced almost automatically. The benefit is enormous in terms of time and effort required to properly implement the change. Second is to enable a full production system where the preparation of shop drawing is driven by the production sequence. Short lead time reduces the system inventory of design information, making it less vulnerable to change in the first place. Shop drawings are produced once a majority of changes have already been made. This minimizes the likelihood that additional changes will be needed. In this lean system, shop drawings are produced at the last responsible moment. 3. To make prefabricated solution viable in projects with restricted lead times between the contract date and the date demanded for the commencement of on-site construction, which would ordinarily prohibit their use. Often, general contractors find themselves committing to construction start dates with lead times that are shorter than the time required to convert conventional building system to prefabricated ones, due to the long lead times needed for production design using 2 decades. For example, a building design with a cast-in-place concrete structure required, on average, 2-3 months for conversion to precast concrete before the first required pieces can be produced. In contrast, BIM systems shorten the duration of design to a point where more components with longer lead time can be prefabricated earlier. And this is the example comparison between 2D CAD system and BIM. And you can see the comparison from Microsoft project that they estimate time to build a house or office building package. Next is BIM enable process change. BIM's primary contribution for general contractors, subcontractors, and fabricators is that it enables virtual construction. From the perspective of those directly responsible for producing buildings, whether on-site or in offset fabrication facilities, this is not just an improvement, but a new way of working. For the first time, construction managers and supervisors can practice putting the pieces together before they actually commit to the labor and materials. They can explore product and process alternatives, make changes to parts, and adapt to construction procedures in advance. And they can perform all of these activities in close collaboration with one another across different threads continuously and as construction progresses, allowing them to cope with unforeseen situations as they emerge. They can also deal in the same way with changes introduced by owners and designers. Next is generic system requirement for fabricators. Generic requirement common to all type of fabrication and places special emphasis on the need for fabricators to participate actively in compiling comprehensive building models as part of collaborative project teams. The following section expands the list of requirements to include specialized needs of specific types of fabricators. Note that the most basic required properties of BIM platform, such as support for solid modeling, are not listed because they are essential for all users and almost universally available. Next is major classes of fabricators and their specific needs. This section describes specific requirements for fabricators of various kinds. It also provides a short list of software packages available at the time of publication for each class of fabricator. The software packages are listed in table below along with explanation of their functionality for each domain and source for additional information. As you can see, the table shows the information of compatibility and functionality that BIM software has. For example, Tekla structure have the building system compatibility is structural steel, precast concrete, CIP reinforced concrete, mechanical, electrical, plumbing, or MEP certain walls. And the functionality is modeling, analyze, processing, fabrication, detailing, coordination. The source for information Tekla structure can you get from www.tekla.com. And the other example As you can see, there is SDS to design data, StructCAD, Revit structures, Revit MEP, 3D plus structure works, Revit architecture, ASE rebar software, all plan engineering, all plan architecture, CADIA or digital project, Graphisoft archiglazing, Softex V6, CAD pipe commercial pipe, CAD pipe HVAC and hanger, CAD pipe electrical and hanger, QuickPen pipe designer, QuickPen duct D designer, Bentley building mechanical system, Graphisoft MEP modeler, CAD MEP plus, FIB MEP plus, SpringCAD, FrameWrite Pro, MWF or metal wood framer. Next is adopting BIM in fabrication operation. A robust management strategy for the adoption BIM must concern aspects beyond software, hardware, and the training of engineering staff because of its range of impact in workflows and people. BIM systems are sophisticated technology that impacts every aspect of a fabrication subcontractor's operation, from marketing and estimating through engineering, procurement of raw materials, fabrication, shipping to installation on-site, and maintenance. BIM does not simply automate existing operations that were previously performed manually or using less sophisticated software. It enables different workflow patterns and production processes. BIM systems directly improve engineering and drafting productivity. Unless a company experience sustained growth in sales volume through the adoption period, the number of people needed for these activities will be reduced. Downsizing may be threatening to employees whose energy and enthusiasm is critical for changing work procedures. A true plan should account for this impact by considering and making provisions for all staff, both those selected for training and those for whom other tasks may be found. It should aim to secure involvement and commitment at an early stage. Once software and hardware configuration have been selected, the first step will be to prepare a true adoption plan, starting with definition of the goals to be achieved, a selection of the right staff to lead the adoption, both as manager and as first learners. Ideally, the adoption plan will be developed together with or by the selected leaders in close consultation with key people from the production and logistic department company-wide. The plan should detail timing and personal commitment for all the following activities, such as first, training engineering staff to use the software. A word of caution, 3D object modeling is sufficiently dissimilar in concept from CAD drawing that some experienced CAD operators feel the need to unlearn CAD behavior, a serious barrier to effective use of a BIM software. As with most sophisticated software, proficiency is built with practice over time. Staff should not be trained until the organization can ensure that they can devote time to continue use of the software in the period immediately following the training. Second is preparation of custom component libraries, standard connection, design rules, and so forth. For most systems and companies, this is a major task. But on the other hand, it is a key determinant of the level of productivity that can be achieved. Different strategy can be considered. Custom components can be defined and stored incrementally as needed on the first projects performed. A large proportion of the libraries can be built ahead of time, or a mixed approach is possible. Larger companies may elect to dedicate a specially trained staff member to compile and maintain part libraries, because parametric modeling libraries are considerably more complex and sophisticated than those used with 2D CAD. Third is customization of the software to provide drawing and report templates suitable for the company's need. Immediately after training, the first learners can be tasked with ghosting a project. This involves attempting to model a project that is being produced in parallel using the standard CAD software. Ghosting provides an opportunity to explore the breadth of a real project, while not bearing responsibility to produce results according to production schedule. It also reveals the limitation of training and the degree of customization that will have been achieved. And last is and five seminars and or workshops for those impacted but who are not direct user, other department within the company, raw material and processed product suppliers, providers of outsourced service and clients, to inform them of the capabilities and list their support and solicit ideas for improved information flows that may become possible. In one such seminar at a precast concrete company, the manager of the river cage assembly shop was asked to comment on various options for sub-drawing dimensioning formats. Instead, he responded by asking if he could have a computer for 3D viewing of rebar cage color-coded by bar diameters, which he felt would enable his team to understand the cage they were to tie in a fraction of the time they currently needed to interpret 2D drawing sets. And that's all for my presentation. I'd like to thank you and for your attention and time. Sorry for my mistake. I appreciate all of you guys. Thank you.